Hi folks, in this problem we have a gun which fires bullets, let's say at 200 meters per second, and there is a target, this is our target, which is on the same horizontal level as the gun. The question is, at which point above the target, that is, at what height h above the target, should the gun be aimed so that the bullet flying in its parabolic path hits the target? We can easily solve this problem using the range formula, but I'm going to use this opportunity to derive the range formula. First, what is the range? The range r is the distance from the point of projection to a point on the path of the projectile which is at the same level. So, the displacement in the y direction is 0 when we calculate the range. So, let's do our usual thing. We'll set up our x-axis and y-axis, and we'll set up the directions separately, x and y, x to the right and y vertically upwards. Ux, let me first write it down in terms of general variables. Let's say the initial velocity is u at an angle of theta. So ux is u cos theta and uy is u sin theta. Ay is minus g, acceleration due to gravity, and ax is 0. Sy is equal to u sin theta t plus half at squared, so minus half gt squared. And this should be equal to 0 when we are calculating the range. And Sx is the range is equal to u cos theta t. Now from this equation, what do we get? I'm going to write it down here. U sin theta t minus half gt squared is 0. That gives us two values of t. T is equal to 0 satisfies the equation, and also 2u sin theta by g. Now obviously at time t equal to 0 also sy is 0, and it is 0 again at t is equal to 2u sin theta by g, and we substitute that into Sx, and that gives us the range. So the range is u cos theta times 2u sin theta by g. And that, my friends, gives us the range formula, which is u squared. 2 cos theta sin theta can be written as sin 2 theta divided by g. So given the distance of the target from the gun, which is on the same level, and given the initial velocity, that is the velocity with which the gun fires the bullet, we can find the angle from this formula. So sin 2 theta is equal to gr by u squared. And once you get theta, all you have to do is use tan theta is equal to h by r to find the height h of the point at which the gun should be aimed so that the bullet hits the target. So let's apply our range formula to solving this particular example. A gun is capable of firing bullets at 200 meters per second. 40 meters from it at the same level there is a target. Question is, at what height above the target should we aim the gun? So we start with this formula. So we have sin 2 theta is equal to g times r by u squared. So that is equal to 10 times 40 divided by u squared, that is 200 squared. And this turns out to be 1 by 100. So now all we have to do is use our calculator or sine tables to find out 2 theta. 2 theta is of course sine inverse 1 by 100. I'm going to leave that for you to find out. From this you can find out what theta is, and then from that you find tan theta, which is equal to h by 40. So the answer h is equal to 40 tan theta. So that takes care of this problem. But before we move on, I want to show you something very interesting. Notice that sine 2 theta is very, very small. So for small angles, there is an excellent approximation that we use again and again in physics that you should learn. Consider a circle of radius r. Let us drop a perpendicular so that we have out here an angle theta, and the perpendicular is the opposite side for the angle theta, for this right angle triangle. Now let's also assume that theta is very, very small. If theta is very small, you can convince yourself by looking at the drawing that the length of the opposite side is practically the same as the arc length. So the opposite side, O, is approximately the arc length, which is r theta. The hypotenuse, h, is r. So sine theta, as long as theta is very small, is to an excellent approximation the opposite side divided by the hypotenuse, which is theta. But keep in mind that we use the fact that the arc length is r theta, arc length s is r theta, and that is true only in radians. Again, this is the definition of theta in radians. So all this follows, that is, for small angles, sine theta is approximately theta as long as theta is in radians. Be careful. As an example, 1 degree is a small angle, but sine 1 is not equal to 1. Sine 90 degrees is 1. That's because this relationship holds only in radians, not in degrees. So if you want to talk about 1 degree, you first convert it to radians. How much is 1 degree? 1 degree is equal to pi by 180 radians. And so sine 1 degree, which is equal to sine pi by 180 radians, is approximately pi by 180. That's because pi by 180 is a small angle. So you can do this only in radians. Now while we are at it, notice that the adjacent side is also practically equal to the radius, which is the hypotenuse. So cos theta is approximately 1, and tan theta is again opposite side by adjacent side. The opposite side is r theta approximately, divided by the adjacent side, which is approximately the radius. So that is equal to theta, again in radians. So in summary, keep this in mind. As long as you measure theta in radians for small theta, sine theta is approximately tan theta, which is approximately theta in radians, and cos theta is approximately 1. Now these relations we keep using again and again in physics. So let's go back to our previous problem. So in this problem, notice that sine 2 theta is 1 by 100. So as long as theta is measured in radians, this is very small, so we can assume 2 theta is very small. So if we do that, then sine 2 theta is approximately 2 theta. So 2 theta to an excellent approximation is 1 by 100. And so theta to the same approximation is 1 by 200 in radians. And tan theta is again approximately theta. So that is also equal to 1 by 200. But our tan theta is h by r, which is 40. So right away I get h is equal to 40 by 200, which is equal to, this is in meters. If I multiply by 100, I get 20 centimeters. So we aim the bullet, or rather we aim the gun at a point 20 centimeters above the target. The bullet should hit the target. Let's move on to the next problem. This problem is usually called the monkey and the bullet problem. I'll state the problem first. There is a monkey on a tree. A gun is aimed at the monkey. At the instant that the gun fires, the monkey drops down from the tree. prove that the bullet still hits the monkey. Now we don't want to be shooting monkeys. So I'm not going to call it a monkey, I'm just going to call it a target. Maybe a toy monkey or something is just a target. So the idea is this. A gun fires with an initial velocity u and it's aimed at this target. The target is at a height h above the level of the gun, and the bullet goes in a parabolic arc. The instant that the bullet is fired, the target is released, so it's in free fall. It falls from rest. Now we have to show that the bullet still hits the target. I'm going to prove this in two different ways. First, we'll show this in the ground frame of reference. How do we prove that the bullet hits the target? So at some point of time, let's say t seconds later, the bullet crosses this vertical line. So this at that instant of time is sy, the displacement of the bullet in the y direction. And let's say the time of travel for this is time t. Now we have to show that during this time, the target has come down this distance so that the bullet hits the target. Which means during this time, the distance moved down by the target. What is that? Half gt squared. Because the initial velocity of the target is 0. ut plus half at squared, that's the displacement, and this time I am taking downward as positive, so I get half gt squared is the distance. We need to show that distance is equal to h minus sy, which means the target has come down exactly the right distance so that it meets the bullet. So we need to show that half gt squared plus sy is equal to h. So I'll put a question mark here. Is this equal to h? This is what we need to prove. So in time t, what is the horizontal displacement covered by the bullet? We'll call it sx. So sx is going to be equal to u cos theta t, where theta is the initial angle, this. Now from this triangle, you can also see tan theta is equal to h by sx. So the nice thing about making a drawing is that you can start writing down all the relationships that you can see from the drawing, and they will help you solve the problem. Okay, so we need sy. What is sy? Sy is going to be, again, ut plus half at squared, taking up as positive, u sine theta t plus half at squared, because taking up as positive, acceleration is minus g t squared. If I take this and plug it into this relationship, I get u sine theta t minus half gt squared plus half gt squared. Is that equal to h? That is the question. Well, check it out. We solve for t from this. So this equation gives us u sine theta times t, which is sx by u cos theta. Is that equal to h? U cancels. Sine theta by cos theta is tan theta. So tan theta is equal to h by sx. Yes. So yes, that's the proof. I would strongly advise you sit down and try to prove it for yourself, because this is an excellent problem from which to learn a lot of physics. And go over the proof again if you didn't understand it. Now I'm going to show you the same proof from a different point of view, from a freely falling frame. Let's look at that. This second argument is very subtle and very beautiful, so listen very carefully. So we get into a frame of reference which falls with the target, so that our frame of reference at time t equal to 0, when the gun is fired, at that instant, our frame of reference also has 0 velocity and it falls with the target. In this frame of reference, there is no gravity. So in this frame of reference, a bullet will travel in a straight line with constant velocity. So in this frame of reference, a bullet will travel in a straight line with a constant velocity. And at time t equal to 0, since the velocity of this frame is 0 with respect to the ground frame, the bullet's velocity is the same in both frames. And the bullet is aimed at the target. And in this frame, the target is stationary. So a bullet aimed at the target, when there's no gravity, will go and hit the target. Proof complete. Of course, in this frame of reference, we'll see the gun accelerating upwards with an acceleration g, but we don't care about that. We only care about what happens the instant after the bullet is fired. The bullet moves in a straight line, the target is stationary, and bullet hits the target. Think about it. Well, that's it for this video. I'll see you in the next video. Bye, folks.